On April 10, 2019, 200 scientists released a photograph of a shadow 26,000 light-years away, and it took them 2 years just to confirm the picture was real. 3 years later, the same team released a second photograph, this time of the black hole at the exact center of our own galaxy, 4.3 million times the mass of the Sun, folded into a region smaller than the orbit of Mercury. In between those two photographs, a different set of instruments. 2 L-shaped tunnels in Louisiana and Washington state, each 4 kilometers long, detected a ripple in space itself, produced when 2 black holes collided 1.3 billion years ago and converted 3 entire suns' worth of mass directly into energy in a fifth of a second. We have photographed them. We have heard them collide. We have measured the exact moment gravity itself trembled. And after all of that, after direct images, after gravitational wave detections, after Nobel Prizes handed out in 2017 and again in 2020 for exactly this work, most people who consider themselves scientifically literate still believe something about black holes that no physicist actually believes. And it isn't a small detail. It's the center of the whole picture. Literally. Here's the belief, stated the way a smart, curious person would state it, because that's the only fair way to attack an idea. You state it as strong as its owner would state it, not as a straw man. The belief goes, at the middle of every black hole there is a point, a single point with no size at all, where all the matter that ever fell in has been crushed down to infinite density. This is called the singularity, and the belief is that physics has calculated it, verified it, and confirmed that it's really there, the way physics confirmed the existence of the Higgs boson or the bending of starlight around the sun. It sounds precise. It sounds like the kind of thing a textbook wouldn't print unless it had been proven. And it is exactly backwards. An infinite density is not a measurement. Nothing in nature has ever been measured to be infinite, because instruments produce numbers, and infinity is not a number that comes out of an instrument. It's what comes out of an equation. When you've asked it a question it can no longer answer. When a physicist tells you the singularity has infinite density, what they are actually telling you, in language that got quietly smoothed over for television, is this. General relativity, Einstein's theory of gravity, produces a nonsense answer at that point, and nobody has a theory that produces a sensible one yet. The singularity isn't the most extreme thing gravity does. It's the exact spot where gravity, as we currently understand it, stops doing anything at all, because our description of it collapses into a number that means nothing. I want to be careful here, because this is the kind of claim people mishear as, so black holes aren't real. And that is not what I am saying, and it would be a betrayal of the actual physics to let you leave with that impression. Black holes are as real as anything astronomers have ever observed. The horizon, the boundary past which nothing returns, has now been photographed directly, its shadow measured, its size matching Einstein's prediction to within a few percent. What isn't real, or rather, what isn't known, is the thing sitting at the center that gets described in every documentary as a settled fact. And that gap, between the boundary we've now literally taken a picture of and the center we talk about with total confidence, is one of the strangest double standards in all of popular science. We treat the outside of a black hole as an open scientific frontier, actively being measured. We treat the inside as a solved problem. It's the reverse. The outside is confirmed. The inside is the most unresolved sentence in all of theoretical physics, and it has been unresolved for over a century. Not because nobody's looked hard enough, but because looking harder with the wrong tool doesn't help. To see why, you need to go back to a soldier in a trench on the Russian front in the winter of 1915, a German astrophysicist named Karl Schwarzschild, who had a rare autoimmune skin disease and about 4 months left to live, and who was reading Einstein's newly published field equations for general relativity. 10 coupled equations, so difficult that Einstein himself didn't expect anyone to solve them exactly for years. Schwarzschild solved them in weeks from a military hospital and mailed the solution to Einstein, who read it aloud to the Prussian Academy of Sciences in Berlin because Schwarzschild was still deployed. Buried in that solution was a number, a radius, at which the mathematics did something strange. Certain terms in the equation flipped sign, blew up, or vanished, depending on how you looked at them. Schwarzschild didn't know what to make of it. Einstein, for the rest of his life, believed it was a mathematical curiosity that nature would never actually produce. He published a paper in 1939 specifically arguing that real stars could never collapse that far. He was one of the greatest physicists who ever lived, and on this specific point, he was simply wrong. And knowing that is worth more than knowing the fact itself, because it tells you that being wrong about this exact thing has never been a mark of ignorance. It's been the default position of nearly everyone who's touched it, including the man who wrote the equations. 15 years after Schwarzschild's death, a 19-year-old Indian physicist named Subramanian Chandrasekhar boarded a ship from Madras to Cambridge. And somewhere in the middle of that voyage, working alone with pencil and paper, he calculated that a burnt-out star above a specific mass, about 1.4 times the mass of the Sun, a number that now carries his name, cannot be held up by the pressure that supports ordinary white dwarfs and must keep collapsing. He was 19. He presented the result to the Royal Astronomical Society in London in January 1935, and the most celebrated astrophysicist in the world at the time, Arthur Eddington, the same Eddington whose 1919 eclipse expedition had confirmed Einstein's theory of general relativity and made Einstein famous, stood up immediately afterward and publicly ridiculed the calculation, calling it a mathematical trick with no physical meaning, and declared that nature would surely find a way to prevent anything so absurd from happening. Chandrasekhar was correct. Eddington was one of the most respected scientists alive, deeply expert in exactly this subject, and he was still wrong, in public, with total confidence, about the same category of object we're discussing tonight. Chandrasekhar won the Nobel Prize in 1983, 48 years later, largely for this result. I bring this up not as trivia, but as a pattern you should notice, repeating. Einstein wrong about Schwarzschild's radius in 1939, Eddington wrong about Chandrasekhar's limit in 1935, both of them titans of the field, both wrong in the same direction, both wrong about the same object. If you've absorbed a confident wrong belief about what's inside a black hole, you're in the company of two Nobel-caliber physicists who made the identical kind of mistake, which should tell you something about how naturally the human mind reaches for a solid, definite answer, even when the honest answer is, the theory stops here. That number Schwarzschild found is what we now call the event horizon. And it's worth being exact about what it actually is, because this is where the first real confusion starts. The horizon is not a surface. It's not made of anything. It has no thickness, no temperature of its own, no physical material presence you could theoretically sample if you could survive the trip. It is a boundary defined entirely by geometry, the point at which the paths that light itself is allowed to take all bend inward, so that toward the center stops being a direction you can choose and becomes a direction you're already traveling, the same way you're always traveling toward next Tuesday. Nothing violent happens there, if the black hole is large enough. And here's a fact that surprises almost everyone, including people who've watched a dozen documentaries. You could cross the horizon of a sufficiently massive black hole, one of the billion solar mass giants at the centers of large galaxies, and feel nothing. No stretching, no tearing, no fireworks. The tidal forces that would shred you apart depend on how sharply gravity changes over the length of your body, and for a big enough black hole, that change is gentle at the horizon and only becomes lethal much later, deeper in. You would cross the point of no return with your body completely intact and have no local way of knowing you'd crossed it at all. The reason the horizon works this way, gently for a giant black hole and violently for a small one, comes down to a single piece of mechanism worth actually understanding rather than just accepting. Tidal force, the difference in gravity's pull between your head and your feet, depends on how sharply gravity's strength changes over a short distance, and that sharpness is inversely related to the size of the black hole itself. A small black hole, a few times the mass of the Sun, packs its entire gravitational punch into a horizon only a few kilometers across, so gravity changes enormously over the length of a human body, and you'd be stretched apart, spaghettified, in the term physicists actually use in seminar rooms without irony, well before you reach the horizon at all. A supermassive black hole, like the 4.3 million solar mass object at the center of our galaxy, has a horizon roughly the size of Mercury's orbit, so the same gravitational strength is spread out over a distance millions of kilometers wide, and the change from your head to your feet is negligible. Same physics, same equations, wildly different experience, purely because of scale. Which is worth knowing precisely because most popular explanations show you a black hole ripping a spaceship apart at the horizon and never mention that this only happens for the small ones. For 50 years after Schwarzschild found that troublesome number, nobody outside a small circle of specialists even had a settled name for the object it described. Physicists called it a frozen star, or later a collapsed star, or, following the Soviet convention, a collapsar, each name reflecting a slightly different guess about what was actually happening. In December 1967, at a conference in New York, the physicist John Archibald Wheeler, Richard Feynman's doctoral advisor, and one of the people who had helped push the field to take Oppenheimer and Snyder's old 1939 paper seriously again, used the phrase black hole publicly, and it stuck immediately, spreading through physics and then through the public within a few years. Wheeler always said he didn't invent the phrase so much as adopt, one shouted from the audience, but whoever coined it, the name did something that collapsar never could have. It gave the public an image, a hole, something with an inside you could imagine falling into and reaching the bottom of, and I think that single choice of word did more to plant the solid point at the center intuition than any equation ever did. A collapsar sounds like a process. A black hole sounds like a place. And once you're picturing a place, your mind automatically wants there to be something sitting at the middle of it, the way there's something at the bottom of a well. That fact should make you uncomfortable, and it should also make you ask a question. And I want to hold that question open for a minute before I answer it, because it's exactly the right question, and most people never get to it. If crossing the horizon feels like nothing, if there's no wall, no flash, no sensation, then what, precisely, is different about the inside? If nothing physically marks the boundary, what makes it a boundary at all? Before I answer that, I need to give you the second piece, because the two pieces click together, and giving them out of order would rob you of the click. In 1939, the same year Einstein was publishing his paper insisting collapse to that radius was impossible, two physicists at Berkeley, Robert Oppenheimer, 6 years before he would run the Manhattan Project, and his student, Hartland Snyder, published a paper doing the actual calculation of what happens when a massive star runs out of nuclear fuel and its own gravity takes over. Their paper showed that for a star heavy enough, collapse doesn't stop. It doesn't find a new equilibrium. It doesn't bounce. Every layer of the star falls inward faster than any force can push back, and it keeps falling, forever, mathematically speaking, converging on a point of zero size. Oppenheimer and Snyder had discovered, on paper, in the same year Einstein said it couldn't happen, that it does happen, inevitably, as a direct consequence of Einstein's own equations. Nobody paid much attention. World War I started weeks later. The paper sat almost unread for nearly 3 decades. It took until 1965, 26 years later, for a mathematician named Roger Penrose to prove something far stronger than Oppenheimer and Snyder had shown, and this is the result that actually matters for the question I left open. Penrose didn't just show that a perfectly smooth, perfectly symmetrical collapsing star produces a singularity. He proved, using a new set of mathematical tools, that any collapse past a certain point, messy, lopsided, spinning, imperfect, exactly like every real star in the universe actually is, produces one too. It wasn't a special case. It was unavoidable, built into the structure of general relativity itself, for any object dense enough to trap its own light. Penrose won the Nobel Prize in Physics for this in 2020, 55 years after he proved it, and the citation specifically credited it as the discovery that black hole formation is a robust prediction of general relativity, not a fragile coincidence. Here's why that answers the question I left hanging. What makes the horizon a boundary isn't a wall. It's that Penrose's theorem guarantees that once you're inside it, every future path you could possibly take, no matter what you do, no matter how you accelerate, converges on that central point in a finite amount of your own time. Not eventually, not if you're unlucky, necessarily. The theorem proves that falling toward the center stops being one option among several and becomes the only direction time itself points for anyone inside. That's what the horizon actually marks. Not a place where physics gets violent, but a place where the future itself gets rerouted, permanently, toward a single point that the equations describe as having zero size and infinite density. And there's the trap, right there, in the phrase I just used. The same phrase every documentary uses. The same phrase. I want you to stop accepting the way you've been accepting it. Infinite density is not Penrose's theorem discovering a genuine physical state of matter. It's the theorem proving that general relativity, followed to its logical end, produces an answer that general relativity itself cannot interpret. Density is mass divided by volume. Penrose's theorem shows the volume goes to zero. Divide any positive number by zero and watch what happens to your calculator. It doesn't give you a very large number. It refuses to give you a number because the operation you're asking it to perform no longer means anything. That's not a description of the center of a black hole. That's a description of the exact point where our best theory throws up its hands. This is worth pausing on because it's the whole argument, and I don't want to rush past it just because it's uncomfortable to sit with an answer that isn't an answer. When a bridge engineer's model predicts infinite stress at a support beam, no engineer concludes the beam actually experiences infinite stress. They conclude the model has been pushed outside the conditions it was built for, and they go get a better model. When Einstein's equations predict infinite density at the center of a black hole, the correct professional response, and it is, in fact, the response every working physicist who studies this actually gives, even though it rarely survives being translated into a television script, is that general relativity has been pushed outside the conditions it was built for. General relativity was built to describe gravity as smooth, continuous geometry, at scales vastly larger than individual particles. At the center of a black hole, the theory is being asked to describe a region smaller than an atom, where matter should behave according to quantum mechanics, and general relativity contains no quantum mechanics whatsoever. It was never built to answer that question. The infinite number isn't nature's answer. It's the sound of a theory being asked a question in a language it doesn't speak. So what actually happens at the center? I'm going to tell you the honest state of the field. And the honest state of the field is that nobody knows. And I mean that in the specific sense that there are competing, mutually incompatible candidate answers, actively argued about at conferences, none of them experimentally confirmed. String theory suggests the singularity gets replaced by something like a tightly wound, extremely small but finite structure. Loop quantum gravity, a rival approach that quantizes space-time itself into discrete chunks at the smallest scales, predicts collapse, doesn't reach zero size at all. Some versions predict a bounce, matter rebounding back outward once it's compressed enough, meaning the true center might not be a point but a rapidly rebounding core, small but never actually zero. These two respected, mathematically serious research programs, pursued by thousands of working physicists over the past 40 years, do not agree with each other on what replaces the singularity, and there is currently no experiment that can distinguish between them, because the region in question is causally sealed behind the horizon and small enough that even our best particle colliders are irrelevant to it by dozens of orders of magnitude. I want to be honest with you about something specific, because I think false confidence does more damage than admitted uncertainty ever could. This is the part of the subject where I feel the least settled myself. Not because I doubt black holes are real, or doubt the horizon, or doubt the mathematics of collapse. All of that rests on some of the most tested physics we have. It's specifically the center, the actual final state of that collapsed matter, where I think the field is guessing with unusually good tools, and where I think the confident tone used in most explanations, including plenty I've given in the past, oversells how settled the answer is. If you asked me directly what's at the center of a black hole, the accurate answer is a place where our two best theories of physics, general relativity and quantum mechanics, have never been successfully combined, and until they are, infinite density is a placeholder for our own unfinished work, dressed up to sound like a discovery. That unfinished business has a name: quantum gravity. And it's been the single most sought-after unification in physics for nearly a century, And I promised you a moment ago I'd come back to why this problem is so stubborn. So here's the mechanism, not the mood. General relativity treats space and time as a smooth, continuous fabric that curves in response to mass. Quantum mechanics treats every field as fundamentally grainy, jittery, made of discrete quanta that can never sit still, subject to an uncertainty that isn't a limit of our measuring devices, but a built-in feature of reality itself. At the scale of everyday physics, you can use general relativity for gravity and quantum mechanics for particles and never see them conflict, because gravity is so unbelievably weak compared to the other forces that quantum jitters never matter for it, but compress enough mass into a small enough space. Exactly what happens in the last instance of collapse toward a singularity. And eventually the region shrinks down to a scale called the Planck length, about 100 million trillion times smaller than an atom, at which point gravity's curvature and quantum uncertainty become comparably strong for the first time, and neither theory alone is built to handle both at once. Nobody has ever verified experimentally what happens at that scale. It is, right now, the deepest unanswered question in fundamental physics, and it sits exactly at the center of every single black hole in the universe, quietly, unresolved, underneath the confident narration of 100 documentaries. I said a minute ago that this problem isn't unique to black holes, and here's where the floor of this whole subject actually drops away, because it's not a coincidence, and it's not a minor footnote. It's the same mathematical wound showing up in a second place. Run the equations of general relativity backward in time, instead of forward through collapse, and you get an expanding universe contracting as you rewind it, galaxies rushing back together, until you reach a moment, roughly 13.8 billion years ago, where the same thing happens. The equations predict a point of infinite density, infinite temperature, zero size. We call this one the Big Bang singularity. And it is mathematically the identical kind of failure as the singularity inside a black hole. Not a description of an actual infinitely dense dot that a hypothetical observer could have stood beside, but the exact spot where general relativity, run to its logical limit, stops being able to answer the question we're asking it. The origin of the entire universe and the center of every black hole in the sky are, mathematically, the same open wound in physics, wearing two different costumes. We don't just not know what's inside a black hole. By the identical argument, we don't actually know what happened at the beginning of the universe either. We know what the equations say happens as you approach that moment, and we know, with total confidence, that the equations stop being trustworthy exactly at the moment everyone is most curious about. There's one more piece that belongs in this picture, because it's the part that turns this from an abstract argument about equations into something with actual physical consequences you can, in principle, someday measure. In 1974, Stephen Hawking combined general relativity with quantum field theory. Not full quantum gravity, but a hybrid calculation, quantum fields living on a curved but otherwise classical black hole background, and found something almost nobody expected, including Hawking himself, who initially tried to find the error in his own math because the result seemed absurd. Black holes are not perfectly black. They emit faint radiation, now called Hawking radiation, and as a direct consequence, they very slowly lose mass and, given enough time, evaporate completely. For a black hole the mass of the Sun, that time is about 10 to the 67 power years, a number so much larger than the current age of the universe that writing "the universe is 13.8 billion years old" next to it makes 13.8 billion years look like less than a single second on that scale. And here is the open question that this discovery created, one that has occupied theoretical physicists for 50 years and is still not resolved. If a black hole eventually evaporates completely, disappears, radiates itself away to nothing, what happened to everything that ever fell in? Hawking's own calculations suggested the radiation coming out is purely random, carrying no information about what went in, which would mean that whatever fell into the black hole, a star, a spacecraft, a person, a book, is genuinely erased from the universe's history, information destroyed, not scrambled but actually gone. That directly violates one of the deepest principles in all of quantum mechanics, the idea that information can never truly be destroyed, only rearranged. Physicists call this the black hole information paradox, and it has produced entire research careers, a public bet between Hawking and fellow physicist John Preskill that Hawking eventually conceded in 2004, and, as of right now, no fully agreed-upon resolution. The attempt to fix it produced a second crack that's arguably worse, and I think it's worth walking through because it shows how deep this goes. If you try to preserve information by assuming it leaks out gradually, encoded subtly in the Hawking radiation rather than destroyed, a group of 4 physicists, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, showed in a 2012 paper that you run into a different impossibility. 3 separate, individually well-established assumptions turn out to directly contradict each other. That falling through the horizon of a large black hole should feel like falling through empty space, exactly as I described earlier, that information is never truly destroyed, which quantum mechanics demands, and that Hawking's original calculation of gentle thermal radiation is correct. Take any 2 of those 3, and the physics works. Take all 3 together, and the mathematics forces a contradiction, which led the authors to propose, reluctantly, that maybe the horizon isn't gentle after all. Maybe there's a wall of extraordinarily high-energy radiation sitting right at the boundary, a firewall, that would incinerate anything crossing it instantly, directly contradicting the smooth, uneventful crossing that Einstein's own equations, and 80 years of physicists after him, had always assumed. Nobody in the field is confident the firewall is real. Most physicists suspect the actual resolution is something else entirely, something involving how information might be encoded in the geometry of space-time itself, rather than smuggled out particle by particle. But 13 years after that paper, there still isn't a consensus answer. And I want to be direct about what that means. 3 of the most well-tested ideas in physics, held up next to each other, at the one place in the universe where you can actually test them against each other, currently do not fit. None of this is standing still, which is worth saying plainly, because unresolved is not the same as abandoned. A space-based gravitational wave observatory called LISA, a joint project of the European Space Agency and NASA, is scheduled to launch in the 2030s, specifically to detect the mergers of the supermassive black holes at galaxy centers, the kind whose horizons are gentle enough to test general relativity's predictions in a regime we've never directly probed. The Event Horizon Telescope collaboration that produced those 2 photographs is already working on a next-generation array, adding more telescopes across the planet, and even proposing satellites in space, aiming for images sharp enough to see structure near the horizon that the 2019 and 2022 images could only hint at. None of these instruments will see the center. Nothing built from atoms, however cleverly arranged, can see past a boundary defined by the impossibility of light escaping it. But every one of them tightens the net around the boundary itself. And a boundary measured with increasing precision is exactly the kind of evidence that eventually forces a choice between string theory's tiny finite core and loop quantum gravity's rebounding one, or reveals a third answer nobody currently has the mathematics for. This is not a closed case gathering dust. It is one of maybe 3 or 4 places in all of physics where an actual answer, a real experimental verdict, might arrive within the working lifetime of scientists alive today. I want to bring this back to where we started, because everything I've just walked through was never really a detour. It was the argument, assembled one load-bearing piece at a time. The reason infinite density at the center survives as public knowledge, unchallenged, while every other part of this story gets treated as an open frontier, is that it sounds like the kind of thing you're not supposed to question. It has the vocabulary of a confirmed result. It uses the word infinite, which sounds maximally certain, when in the actual physics it's doing the opposite job. It's the theory's own signature on a note that says it cannot go any further. Every black hole in the observable universe, and there are an estimated 40 octillion of them, has, sitting at its exact center, not a confirmed object, but a hole in human knowledge shaped exactly like the hole in human knowledge sitting at the beginning of time itself. We photographed the boundary. We heard 2 of them collide across more than 1 billion light-years of empty space. We have never once, in the history of the species, gotten a real answer to what's actually at the middle. And the reason isn't that the center